again introduce our next speaker, Vitto, who is professor at the Institute of Electronics at the University, and is also affiliated with the Lean Institute in Grenoble. And he will talk to us about 2D nanomaterials, especially 2D nanofiber structures. So.
Thanks a lot for the chairman. Great introduction. And hello, everybody. So it's my great pleasure to be here to show you some slides. Actually, I heard before I came here from Benjamin Sesame yesterday. He told me you guys are all hardcore physicists. So hardcore means really hardcore. And I just noticed that. I prepared my slides in a very casual way, and it's going to be super fundamental about experiments. But anyways, I think you guys, theoreticians, always have good questions. So I did my PhD approximately like 10 years ago in the Institute in France. So that's where I met Michel Feigelman. And it's really wonderful that he invited me to show you, to be here to show you a review to the backwards of time of how the state of the art and the perspectives of 2D Waals heterostructures. And today I'm going to basically discuss with you how this story was, the whole story was invented. And I'm pretty sure that you have seen that story before many times on the internet, but this is just my personal way to view how the story was developing. And during my presentation, you can stop me and we can interact anytime if you like, okay? So now we play a little game. So let's take a time capsule. So this is where we are today. So the first point of time, I would like to bring you back to, say, 1959. That's great. At that time, people have no way to really have great tools to investigate very thin, very tiny atomic structure, and nobody knows anything about graphene experimentally. So, but people have their great brains. They have we have the good physicists. They have a thought about there's plenty of room at the bottom. What does that mean? That means even though at that time people are mainly studying 3D bulky materials, but there is a way that people can imagine how we can break down the materials from 3 dimension to 2 dimension and to 1D and to 0D. But at that time, nobody could do the experiment, so we will see why. And there are some limitations. So Richard Feynman said this, proposed this famous statement, and if we go that to the fact of 2-dimensional systems, that will be how would the electron structure look like? The first question. So this plenary room at the bottom, that means how would this electronic structure look like? That's a fundamental question first. And then how to engineer, how to control them. I mean, control means really to control in many senses. For example, the strength, the way to stack, and how to make them into nanostructures, to study a lot of physics with a real 2D, let's say, approximation. But you know, because there's always a thickness of atoms, you will never get a real 2D, but very close to. So at that time, Richard Feynman proposed this question. So let's come back today again. If you are Richard Feynman, or you are the great minds in the past decades, so let's review what kind of material, thickness you can imagine. Can anyone name me one or two?
Graphene.
Right, graphene. Yeah, that's because you are traveling from the future, right? At that time, nobody knows, but still, we have in our daily lives very thin materials, thin objects. For example, the A4 paper. So that is already like 80 micrometer. So that's a diameter of average size of our human hair, okay? So there's also wings of bugs. You know, when you slap, you kill the mosquito, you study the thickness of his wing, it will be down to 0.5 micrometer. That's nanometer scale already. So nature creates nanostructures from the very beginning, you know, after this Big Bang, okay? And then we have also handcraft materials like gold foils. So these things, people found that they can go down to 50 nanometers. That's almost state-of-the-art thin film that we can obtain nowadays. Okay, so this is purely made by hand, nothing big deal, just hand. Because gold atoms, they are very good. The ductility is very good, so you can really press them, extend them, and down to very thin thickness. Also, when we were young, when we were kids, everybody's playing with soap bubbles. Soap bubbles, if you look into thickness, and there are indeed some theoreticians and experimentalists investigating this problem, you can find a number of papers reporting that the thinnest thickness of soap bubbles would be 10 nanometers. So that's really, really tiny scales. So these are materials created by, say, nature, so there's no physicist at all, so there's no experimentalist or whatsoever. But these materials, they are kind of not controlled. So people want to do something in real, in experimental rooms and in industry, of course. So in early 17th century, people already found that if you heat up some kind of metal and you evaporate them in vacuum, so that's because thanks to the development of vacuum technology, of course, and then you put a target material on top of this heated target, you will collect a thin film out of that. So this thin film has developed a long time from a very old-fashioned thermal evaporation to sputtering and PLD, which is post-laser deposition, and then later on, which we'll go through further, chemical vapor deposition, a very cheap way but a very facile method to create large amount of two-dimensional materials specifically. There's also a very dedicated machine called a molecular beam epitaxy. So this technology has some limitations. Of course, before this discovery of graphene, everybody was doing these techniques to create thin films. So for example, MBE, it's great. It can create atomic thin materials, including graphene, okay? But there's a very stringent condition to obtain thin films using this MBE technology. That is this lattice match. If you have a large lattice mismatch, then you cannot grow the materials on the substrate. So that's why it's called epitaxy. So this means some kind of duplication of lattice from a substrate to a target material. So this is the thin film technology up to date so far, major technology that we can name. And then here comes our first question of this casual lecture for today's afternoon. How was the first atomic layer material discovered? Does anyone know that question? If no, how the first atomic layer material discovered? Theoreticians like you guys, hardcore guys, predict that 2D materials should not exist at all in early 1940s. There were famous papers working on that because these instabilities of z-dimension of fluctuation, no material should exist in the form of 2 dimension. So that's a famous prediction. And experimentalists like me are dumb guys, so they believe that. So nobody really looked into atomic thick layer materials until very late. Actually, this is a very good example. For example, when you do some cooking at home during the Saturday or Sunday, so you chop off a potato, you find that with a 3D bulky material, you can do subtractive manufacturing into the slices of 2-dimensional quartzite, and then you can also chop off again the slices into 1D little stripes. And if you want to do those match, then you can cut them into 1D to 0 dimension, which is again quartzite. Okay, so this is the way that nowadays everyone is doing to exfoliate layered compounds. We call that subtractive manufacturing. It's just a big name. Actually, nobody can actually, even today, exfoliate graphene into nanoribbons. You can't. You cannot even chop off nanoribbons into nanoquantum dots. You cannot. You have to use other technology like etching, lithography, or epitaxy along the steps. Okay, so that's the limitation. But this gives us some hints. For example, if we have some compound which is already layered, probably you can just exfoliate them by some forces to get really subtractive manufacturing of 2D materials. That's the first thought, okay? But who is the first one to do the experiment? And there are smart guys already there. For example, Professor Pelikan he's now in Harvard. He used to be a professor at Columbia University. That's where I did my postdoc. with Corradine. And he did some very famous experiments based on this idea shown in the previous slides that if there is some compound which is already layered, of course, the most famous one would be graphite, that everyone knows that. And then, so he managed to fabricate a tiny nano pencil. So that's actually a pillar which is made of graphite. Of course, you have to obtain this one, you have to use very advanced technology like lithography to etch them down to this cylinder shape. And then if you put this cylinder shape of graphite, of course you have to choose very carefully to align them. See that the axis is perpendicular to your cantilever, and you scan your cantilever on a substrate. And then that's what they got under a microscope. So under microscope, you saw some nano pancakes. And that's already a big deal at that time. But they're still not atomically thin. They are still Witten thickness. Okay? They are quasi 2-dimensional, but actually they follow the bulk electron wave functions. But that's a good sign. Okay? People can exfoliate graphites on the substrate. And then there's also, we have to, before we go to this big discovery, we have to review that there are several bonds between molecules and crystals. One of them, a group of them has stronger bonding, another group have weaker bondings. Among them, there is a very famous one which is called Van der Waals force that is following some complicated London dispersion and other dispersions together. You know, even today, it's still a complicated question. Anyway, at the end of the day, we got that the force of Van der Waals is proportional to 1 over r to the 7th. That's a very short-range interaction, of course. And if you go to too close, that's actually a formula describing two molecules. If you go to too close to each other, then you have a repulsive. For the repulsive minus the attractive force, you get a very famous one that everyone is learning that from high school physics. So this is the energy potential, how it looks like. People call it Leonard-Jones potential. And again, if we go to the nature, if you grab a gecko and you look at his foot under microscope, you will see that all of this complicated structure looks like a kind of theater and spatulae structure. That means you have a little pad at the end, which is supporting the whole weight of him. Also spiders, even some little bugs. You see that they have very similar structures. Basically, what they have is a large surface and a low weight. So Spider-Man can exist provided that Spider-Man, if he's let's say use some gecko tape, his own weight has to be small enough to support this to compete with the forces. So this is how this the whole story was seen at that time, and we can have an estimation of the strength of these forces. They are ranging from 0.4 kilojoule per mole to 4. That is like 1 or 2 orders of magnitude lower than chemical bondings. So very weak. People can break them by hand. And also, so if we have, like, again, this broad view to all these compounds of layered structures, already now people have more than 5,000 types fabricated experimentally. So there's so many options for us to choose. But why? Nobody ever at that time to start exfoliating them. Because you need something which is really magic. You need to see that thing, and you have to have a good method to exfoliate. So the first experiment was done really easy. Like if we look into that story now, it looks even ridiculously simple. Like you just take a scotch tape from any kind of shop, any kind of supermarket. Then you exfoliate some kind of graphite. Of course, it has to be layered, single crystal or crystallized structure. Then you just fold them several times. You press on a silicon oxide wafer, and under the microscope, you will see a very thin film. So when the two experimentalists first found that structure using this technique, nobody even believed that. People are thinking this isn't possible because theoreticians predict that no 2D material should exist in nature, and how can you obtain that? And the technique is rather simple, because there is another thing we have to pay attention to, which is graphene the material. For nowadays, we know that the absorption of light of each layer is actually quantized. So it's proportional to pi times alpha. Alpha is finding the structure constant. Finding the structure constant is a magic number. So if you use pi times alpha, using this kind of approximation, each layer of graphene is absorbing 2.3 of light. And also, you have to be lucky to use kind of good wafer, because when you put these thin films on top of silicon oxide wafer, you have light incident twice from the top surface and at the interface of silicon oxide and silicon, and then there is a destructive interferences of light. Also, then you will get some kind of competence between the interference. So luckily, Gaiman Novoselov was using a 300 nanometer thickness wafer. They didn't do any screening. They didn't choose that on purpose. They just grabbed one from their old stock from the shelf of their lab. We have this wafer, let's give it a try. And at the end, we got very thin films that we can see with bare eyes directly. And if you choose, for example, like 200 or 500 nanometers thickness silicon oxide wafer, you will have missed it. So that's how it was discovered in 2024. Already here. It's not 24, sorry, it's 2004. So the first graphene, let's say, transistor, field effect transistor was discovered. And there is like a whole half a century there. Nobody really did experiment. There must be a reason, so it's kind of luck, let's say. Gaiman Novoselov studied that system, and they found that the mobility of this magic two-dimensional graphene material is very high. There is a very strong dispersion, and all these materials, all these properties are really new to both theoreticians and experimentalists. So there's a big bang of literature coming out. There's really a delta function if you look at the publication and the history. And this paper has been cited like 75,000 times. So more than many people's lifetime total citations of this one single paper. And then you can see that actually graphene is not new at all. If we look really dig into this literature, the growth of this material has been started in even 1992. There is a surface science paper. They did HCM studies of single layer graphite. They don't even call it graphene material because nobody really paid attention to that. But this is graphene. You see the honeycomb lattice is well produced on platinum 111 surface, and that's a very, very good example of how people obtain graphene using experimental techniques. Also, yes?
Why was the wafer thickness relevant for the discovery of graphene?
Oh, why the thickness of the wafer is relevant? Yes. Because on usual wafer, what we're using is called oxide on top of silicon. So there's a thickness around like from a few tens of nanometers to a few hundred nanometers of oxide on top of silicon single crystal. Let's say there's an index of crystal under there. And at this first surface you have air here, and the second one, this is transparent. This is like the polystone is a mirror, basically it's a mirror. You can take that as a mirror. The light comes down, and then you've got twice the reflection. There is some condition that you have a constructive and destructive interference of the light, and plus there is a thin film of graphene on top. So the absorption is about 2.3% per layer. And if this is really one layer, at some point, if you have say, destructive interference, you don't see that. With the visibility is really low.
The outside thickness is also dependent on the wafer thickness?
Yes. So from the factory, they produce different thickness for other purpose. It's not made for graphene. It's for just any kind of transistors. You need a backgate, for example. If you dope them with kind of electrolyte balls, then this whole substrate is conductive, and this one has a dielectric property. You can fabricate another graphene, any kind of semiconductor FET directly. So this is a MOS structure, how it looks like, reverted backgate. Okay. Okay. So there is also experiments in 2008, very rapidly after this this famous guy Waals science paper. It's like 4 years later, people have developed a lot of different facilities to grow graphene, especially on kind of this iridium, gold, and things like that. So people have found that it's really easy to grow graphene actually. So you just decompose from some methane or any kind of carbon precursors, and these carbon precursors will be decomposed, and carbon will be recombined by sp2 bondings and form this honeycomb lattice of 2D and down to monolayer. So nowadays it looks very easy, but growing graphene on top of a metallic surface is not that really useful, because we need electronic devices, which is, say, not shunted, right? If you grow graphene on top of copper or on top of iridium, and all these substrate is more conducting than graphene. You don't detect anything except for that you can see the morphology of graphene. That's not very useful. So people found that maybe you can get rid of this substrate, and that's the first experiment. One of the very first experiments from MIT, Professor Zheng's group. What she did was like growing CVD graphene on top of nickel surface. And then you can see that, so here there is a homogeneous graphene layer, which is a few layers covering everywhere. And when there is a silicon oxide, there is no graphene. When there is a nickel, there is graphene. Because at that time, graphene growth, they need a catalyst. This kind of carbon precursors come to this very hot chamber, and they can be decomposed, forming these adatoms everywhere. But on the surface, you need some really help of catalytic kind of surface to really form a layer of graphene. So graphene can only form on top of nickel, not on silicon oxide. And then what they do is just dissolve this nickel by some kind of chemical solvent very easily. You can find any kind of acid to dissolve nickel, and then you can transfer graphene on top of silicon oxide. So now, these two different silicon oxide wafers. Now people can find graphene on top of an insulator, right? Of course, this is still transferred by chemical method, and that's the big deal from 2009 that people can transfer that. The first transfer. And then people, a lot of good cookers, like cooks, from experimentalists, has found that actually there are a lot of materials, metallic materials, which can form graphene layers on top of that. But there is a very important parameter, which is the solubility of carbon atoms in the bulk. The lower the better. Why? Because you don't want to precipitate very thick graphene layers. Like this one is already thick, because nickel somewhere is not plotted there, but there were some other materials. For example, for copper, it has very low carbon solubility at around 1,000 degrees C. 1,000 degrees C, that's a hot temperature. So then people found that maybe if you grow graphene on top of copper, it might be better in terms of thinner layers, and that's indeed people found. So this is the cartoon. You can see that the methane is decomposed by 1,000 degrees C temperature, then it sticks to the substrate. Now it's almost anything, but at that time it's only like nickel, copper, and gold, and iridium, things like that. And then the carbon adatoms will form this sp2 bondings to form a graphene homogeneous layer. And then there's also famous experiment from UT Austin, Professor Rodney Wolf. He found that if we do in the alternative manner to grow graphene in terms of isotopic of carbon-12 and carbon-13, then you can just feed some carbon precursor from carbon-12 and then stop the growth, and feed another kind of isotope of carbon-13, so that these two materials have different Raman spectroscopy. So they have carbon, because this mass is different of atoms, this phonon modes are different in terms of energy. So you can really do the mapping in real space and see how this crystal will grow. And if you do this 13 plus 12, you don't see anything, you just see some wrinkles. If you decompose the spectroscopy into carbon-13 and carbon-12, then you can see that the grains are actually stick together, and there are different shapes of grain. And the greens colored one and dark ones are alternative growth from carbon-13 and carbon-12. You can also see that it's becoming slower when the rings become larger, right? So this method is a very good way to trace how this carbon-12 12 or carbon-13 are decomposed and formed into these multi-crystalline graphene layers. And that's a very good example of people using the very advanced tools like Raman, like CVD growth, and to study the dynamics and how this 2D materials is formed in a very hot furnace down to one atomic layer. Then there is also big progress in 2009 there. People found that actually using this transfer method, this is from, I think it's from also Professor Voyev's group in 2009, they published a great paper in Science. So using this copper method, they obtain a grains of 2D material, which is carbon, which is graphene. And then if you grow enough time, all these grains, they'll merge into a single sheet, which is fully covered, 100% coverage of graphene. Then using this wet etching method, you can transfer this from copper to silicon oxide. And then once you do that, you can have also source and drain and gate patterned by the standard lithography method. Then you will have this graphene transistor, exactly like Gaman Novoslov was doing in 2004 using exfoliation method. And also they have very good mobility at room temperature, it's about a few thousand. So this makes people very excited, because before you can only exfoliate very small flakes from labs. Now we can grow them on a large scale, and that's a big breakthrough at that time. Let's say CVD transistors. When we say FET, it means field effect transistor. It's a gate, oxide, and semiconducting channel, like the one shown there, just the source and drain there. And you can do a lot of transport experiments, anything you can imagine. So maybe you have already noticed that the graphene flakes, when you do CVD growth, they have different shapes, right? They have flower-like, they have hexagonal shape, so sometimes they can have irregular shapes. That is purely dependent on the thermodynamics of CVD growth. So you just by tuning this partial pressure of different gases, and you will get different shapes of graphene. That's already well-known phenomenon. So this is how people transfer graphene from a metallic surface to an arbitrary surface, let's say. Basically what people used at the time was some kind of iron chloride, sodium sulfide, and things like that. These are just very mild copper agent. It etches copper at a very low, let's say, rate. So over a few hours, then you'll get a very continuous film of graphene. Of course, there is a protecting, supporting layer on top of that. Graphene is reported to have a very, very strong Young's modulus, but yet it's very fragile. So that's a little bit contradictory. So people have to use a supporting layer, even nowadays, to transfer two-dimensional materials. Then you just dissolve that on the acetone. So again, you will have a very clean one. Looks clean, but if you look at under the microscope, you will see there are a lot of cracks and holes and many residue of PMMA, for example. So this is the way how people do graphene production, even nowadays, sadly. So that's the way it is. And then people, they want to really enhance the method, for example, to create some cleaner way or faster way. So this is an example in Nature Communications 2012. It's already a little bit later than 2009. We see that people found that if actually we put electrode voltage between two plates, metallic plate, one of them is graphene with PMMA coating, the other one is any kind of electrode. Due to these electrochemical reactions, the water will be decomposed into hydrogen gas and oxygen gas. So these hydrogen bubbles, it happens only at the surface of, for example, this platinum or copper or anything. If you control the way of how to feed the current and the voltage, you can really get rid of this PMMA graphene layer by just bubbling this little solvent. And at the end, you will make this PMMA supporting graphene floating on your beaker, and you can just fish them and transfer them onto any kind of substrate. Here is silicon oxide, before and after. So you can see that the color is very homogeneous, and that's the way it is. Also, people found that maybe using this thermal release tape, it can also help to transfer graphene. And that's a very important technique, because without transferring graphene from a metallic surface, nobody can do any kind of transport experiments. You can just see that. You cannot probe any kind of direct thermal behaviors like I will introduce you later in the slides. And now people found that actually if you do a different way of chemical vapor deposition, for example, plasma enhanced, and then you can actually deposit graphene directly on top of silicon oxide. And that's another story, but at that time people were using this kind of transfer technique. So in 2010, which is the year I entered my PhD, Samsung published a very famous paper using this wet transfer technique. You know, they enlarged, they have enough money and enough people to do this experiment. Enlarge this transfer into a wall-to-wall method, and they grow graphene on larger scale of copper foil, and they do a very complicated machine. At the end, they can get a 30-inch film of graphene, like this one. So they even demonstrated a touch screen using graphene. And that one is, it makes people really excited for the future of graphene in 2010. You know, I was just starting my PhD, like probably some of you guys' age. So it's like 14 years ago already. So this technique is very important, and sadly, even now, people have no better ways to transfer graphene. That's the state of the art, seriously. Okay. Okay, then there's a big race of graphene cooking recipes from here to later on days. So, and all these cooking recipes have made people thinking that graphene is going to be used very soon, probably tomorrow. And then in 2010, the Nobel Prize Committee just found it's time to give a Nobel Prize to and Andre at that time. And they won the Nobel Prize in 2010 for their discovery of graphene flakes. And as we said, graphene was not new at all, but they are the first to exfoliate them on a very proper thickness of silicon oxide, and they managed the way to measure the electronic properties. Of course, they are hardcore physicists. They understood the behind the direct dispersion and direct Hamiltonian, all the things behind. And if you look into the literature, even nowadays, people are still doing graphene growth. For example, there is a Nature paper and a Science Bulletin paper. People found that if you use a copper single crystal 111, this kind of foils, you can grow graphene aligned automatically, and eventually they merge into a single crystal graphene up to meters square. This is really a centimeter, and it's really long. People can, if you Google a bit, you can find that there are 100 meters graphene tapes for sale. I don't know what to use for that, but they are available on the market. So people then continue to improve their method to let's say, increase the quality of graphene flakes on top of silicon oxide. And there was some recent development, I think this is last year. They found that some kind of photoresist treatment can neutralize graphene and make them more homogeneous with better quality. So, for example, this is what they get. Sorry, I forgot to put the reference there somewhere. Anyway, you will see that if you put the keyword proton-assisted treatment decoupling graphene, you'll find the paper. Okay. So what they got is they have really homogeneous monolayer graphene to wafer scale, and the mobility is pretty high. You can see that they have quantum hole plateaus at very high temperature. That means the quality is really good. Still, it's just experimental works. Okay. And how people are trying to industrialize graphene. They are trying really hard since 2 decades. You know, since the day of this paper, everyone is trying to, say, produce large-scale graphene and try to sell, I don't know to whom. For example, at least industries are really trying to enlarge the facilities. This is like 10-meter long machine to produce graphene on copper. So it's still the same old method 14 years ago. And there are also some other companies. This one is the one in Beijing. What they do is just basically another version of the Samsung wall-to-wall technique invented in 2010. So magically, we found that all the industry are selling machines to grow graphene, but not the product of graphene. So that's a very interesting phenomenon. And we know that graphene is believed by many theoreticians and experimentalists to have a lot of beautiful properties optically, electronically, even biologies. And some papers reported that graphene can be used for like desalinization of seawater, which is very good for sustainability of human civilization, supposedly. But the question, second one for today is why nobody can buy anything from the supermarket made of graphene so far? So what has been holding back graphene from application? That's the big question. Can anyone name the reason for that? No? Experiment, please. Now we're in the history. You are taking the time capsule. You're traveling back to the. Please go ahead.
Maybe the transfer isn't reliable enough.
That's a very good point. Transfer is not very reliable, and why? They made huge machines for selling. Why still not very reliable? Okay. And any other reasons for that? Like, no.
People still do graphene by exfoliating and extracting process.
Yes.
To have a good piece of graphene, we need to do it a lot of time. How we will establish something for the application if we still make graphene pieces in different processes.
But we just saw the paper in last year that using this proton assist method, PAT method, you can have really homogeneous graphene flakes. Why? So nobody have been using that for nanoelectronics, sensors, or anything. Why so? So there's some deep fundamental problem there, right? So I would say for nanoelectronic applications, the big bottleneck is it lacks of a band gap, right? So for transistors nowadays, if you look into your computer, your cell phones, there are many billions of transistors in there built in your chips, but all of them has a very good on-off ratio and a very good on-state and off-state. That means there is a band gap somewhere. So that's a semiconductor application that you need is you need to have a switch from really good insulator to really good conductor. Graphene has one of the property. It can switch from some kind of peak of resistance to good metallic state, but it cannot really turn off the conductivity. So the conductivity is always there, and that's because of the band gap is missing somewhere there. And that's why we're gonna go through the next sections of this talk. So it's fundamentally thing behind of incapability of being used for graphene. So far, let's be optimistic, not to be pessimistic. So far, graphene is not being used. But there is a good reason already that it's somehow vulnerable to environment. It's easy to get doped. You have a graphene sheet there. Today, the direct peak is at 4 volt. But 2 days after you come back to check it again, direct peak might be minus 4 volts. So this kind of thing, you don't want that in the industrial application. And second, there's a massive band gap. So let's see now it's your time. You should let me know all the details of the calculations. So the block wave tells us that a free electron, so it's p squared over m dispersion. It's a parabolic one. As long as you put this electron in the periodic potential, then it will have this Brillouin zone, which breaks down this continuous dispersion into several band structure, because anywhere the band crosses, there's a little interaction and opens a little band gap at this edge of the Brillouin zone. And that's very simple. For graphene, let's see why there's a missing of band gap there. So this is, I guess many of you already knew that result. Let's just go through that again. We have a real space honeycomb lattice of graphene, which is written, let's take any kind of origin there. We have several vectors, A1 and A2, and delta 1, delta 2, delta 3, which represents the first neighboring and second neighboring vectors of atoms. If you put them into the reciprocal space, you'll have another set of vectors in the K space, which is basically 2 pi over the real space lambda wavelength. And we have several different set of K vectors down there. If you do some little tight binding Hamiltonians, this kind of algebra, you will obtain a wave function which is Hamiltonian equals to this one. And then you can solve that using this very simple formula which looks like a Pauli matrix, and which is indeed is. So basically, you just get this eigenfunction of that previous matrix, and then you will have an image band written in this form. Of course, this is a type binding taking this approximation of first neighboring atoms. And there is some key parameter, which is T, called hopping parameter. And this hopping parameter is defining how electrons jumping from one side A to another side B. And if you plot that under MATLAB code, you will get some advanced logic like this. So this is not new again. So we found that actually there is already papers in 1947, even before this. There's already PR Waals published a paper in PR, so there's some coincidence there. So the band theory of graphite, at that time, Waals didn't call it graphene, but he considered exactly the same model as what we are seeing in the previous two slides, that honeycomb lattice of atoms, and all these algebra of the mathematics are correct, and he got exactly the same answer that people obtained in more than half a century later. But the unfortunate thing is, at that time, because we know that the experimental tools are not advanced enough, and after publishing this paper, people just forgot that paper. So it was hidden in literatures for years and years. Now everyone knows that one. It has a pretty good citation, by the way. So then we already have that band structure plotted in a 3D manner. It's very complicated. It has some kind of 6 cones. We already see that. How are these cones look like? We use this low energy approximation. That is just taking this, define a new vector as k minus k, sitting at the k vector, and then take a little delta away from there, and you have a new kind of expression from here. And after some kind of calculation, you'll get the eigenfunction like this one. So Hamiltonian becomes Vf, Fermi velocity, times the momentum dot the sigma, which is the Pauli matrix. And then this prefactor Vf is defined simply by the atomic constant and this hopping parameter. The hopping parameter, people already knew that from DFT calculations, for example, and it's around 2.8 electron volt. And the A is a constant of carbon-carbon atoms, which is 0.246 nanometers. And if you run the numbers, you got a Fermi velocity very rapidly, which is around 1.5 to the 10 to the 6. So it's about 1/300 of the speed of light. And this dispersion is exactly the same as photons direct dispersion. And this is the people, the first time when they realized this problem, and people just found that, we started from something non-relativistic, and at the end we got a relativistic particles there. And it's the first time people can really obtain in the experimental technique, using experimental method. If you really do this measurement using experiments, it matches very well. The Fermi velocity of graphene is pretty high, and the mobility is pretty high too. Notice that it's not a particle velocity, it's just a wave function propagating in the log potential. And that's how people can just do the experiment again. Using this previous dispersion, we have cone-like graphene at the low energy limit, and if you tune the chemical potential by a gate voltage, which is a voltage down there, you can move this Fermi level down and up. That means, there is a direct point there. The Fermi level can be tuned simply by some kind of capacitance coupling from the gate. And this is a very, very good example. And by this one, this diagram, people can have a lot of calculations. For example, mu-free path can be defined by sigma h over 2 square of kf, and kf, this one is actually square root of n pi, and the n is coming from this capacitive coupling. And also the diffusion coefficient can be obtained also. And there's one thing we have to emphasize for theoreticians specifically. We know that when we say a gate voltage, I've read papers from theoreticians. They put this potential into Hamiltonians, which mistakenly making this energy very weird and got a strange result. Actually, when you put a gate voltage, it does nothing but inducing some carriers at the surfaces between graphene and the silicon oxide. It's just purely classical capacitive coupling. So this induced carrier density, you can get that with a 300 nanometers thickness of silicon oxide, whose dielectric constant around 4, you'll get per volt. Every voltage you put on a gate, you will obtain 7.8 to the 10th of centimeter minus 2 carrier density. So that means before you break down this silicon oxide, you can have up to 10 to the 13th carrier density in unit of centimeter per centimeter square per volt. And that's how we usually do the experiment. And then again, back to the question, why graphene is not being used? Because there's a lack of band gap, and we have ran this little algebra of how to obtain this Hamiltonian graphene and the dispersion. You know, at the end, actually, graphene is protected by some symmetries. For example, there's a time reversal, and there's a C2Z and C3. That means whatever you do, you stretch, you rotate graphene, and you cannot break this, the band gap. The gap is always 0, so that's why it's called a semi-metal. And the semi-metal ones has a dispersion where at the direct point you have a minimum of density of state. That's why you have a peak of resistance. And there's some kind of efforts of, you know, experimentalists and theorists don't give up. They say there might be some ways to induce gaps in graphene. For example, a good example is that in binary graphene, if you induce a vertical electrical field, then there will be a band gap opening there. Also, people have done some other experiments. The very good examples are the two here. For example, Philip King's group, they managed to etch graphene into very thin nanoribbons, and then there is a localization gap over there down to 1.7 Kelvin. But it's not real. It's not a real hard band gap of kind of semiconductor. It's just due to localization effects. Also, there is another paper in 2010. So people managed to etch graphene into arrays of holes. So it's not a continuous film anymore. It's just arrays of holes etched on top of graphene. The good thing of that is that the IV curve still looks ohmic, so it's still conducting. At the meantime, the direct cone is killed, so it's not a very sharp bipolar behavior. Instead, it's on and off, looks like a kind of a semiconducting field effect transistor. The only thing is that here you have only like on-off ratio of 2 order of magnitude, which is not very good for application purpose. And let's come back to this question of binary graphene again. You can see that if you apply a voltage electrical field, that you can create a little band crossing between this CDM and conduction and valence band. They overlap, and a void crossing forms this so-called Michelin hat structure. And you have a very high resistance peaks at different gate voltages. This is, for example, you know, to create a vertical electrical field, you need 2 gates, a top gate and bottom gate. So that's how you scan this graphene resistance in the parameter space of bottom gate and top gate. So there's an artifact horizontally. This is depending only on BG, so we forget about that one. We just focus on this diagonal one. You can see that the peaks are very high at the 2 corners and lower at this center point, which is the tightly charged point. So this PIL paper is, if you look in the literature, that reports almost the highest resistance we can find, like 1 gigaohm. 1 gigaohm is really insulating. So it means if you put a 1 watt on top of this graphene, at this point you have only 1 nanoampere current. So it's very insulating. But the bad thing is, again, all these insulating areas are very localized. If you scan the gate voltage, there is only a peak. So for application-wise, we don't want that. We want, instead of a peak, we really want some kind of off and on structure like this one. The x-axis is carrier density. So still, graphene can be gapped in terms of vertical electrical field applied to bilayer system, but the gap is not very formed for application purpose. And also people did some very sophisticated experiments of suspending graphene into this kind of structure. So what they did is that they have a binary graphene suspended in vacuum, and then they managed to make a bridge on top, which serves as a top gate, and there's a bottom gate, of course, which is silicon doped ones. So this is a very complicated structure. You have to use very careful experimental tools, for example, to dry this graphene from the solvent's phase. You have to use a critical point dryer, so which is very complicated. At least people found that at very low temperatures, for example, a few Kelvin, that the conductivity of graphene can be really killed, and there is a real insulating phase there. But the temperature is really low, it's a few Kelvins, and nobody can make this happen at room temperature. So it might be interesting for fundamental physics, but so far, for application-wise, it's still far away from what people want to obtain from graphene. So that's why, after all these years of development of theories and experiments, people can still not find any kind of products of graphene and electronics, sadly, so far. So probably you guys, the theoreticians, can find a new way to get graphene. But the symmetry of which protects these K and K prime values are really robust. And to break them, there are very few ways. We will go through that one in the second lecture. That might be some rotational experiment can solve this problem, but that's another story. It's not a band translator anyways. And recently, in 2024, this year actually, there's a paper from Waals AD here. What they published in Nature is that if you grow graphene on top of silicon carbide, they managed to find somehow a broad peak and a very insulating phase, very conductive peaks outside of this insulating gap. So this is somehow the mechanism behind that is not clear enough. There might be some interfacial couplings, please.
Explain again how the top gate, bottom gate measurement is related to the gap.
Oh yes. Okay. So
also 2 slides before.
For binaries, yes. This one.
Yeah.
Yeah. So basically, you have let's forget about the other bands. There are just the two bands. For neutral binary graphene, they're touching each other at one point. If you apply a voltage, which turns out to be an electrical field vertically to this AP plane of binary graphene, you pull down this band somewhere a little bit here, and you pull up the band a little bit up. So this kind of band inversion, not strictly inversion, crosses it, say, will create some kind of hybridization of the two bands, opens a little gap like that. So this is just well-known theoretically and experimentally, and this gap is proportional to vertical electrical field. So let's say this line, the black one, is charge neutrality. Every point on top of this black line is charge neutral. There is no electrons, there is no holes, and away from this point, up and down are electrical field pointing up and electrical field pointing down. With increasing the electrical field vertically, you have larger gaps, so it's always larger. And if you inverse the direction of the electrical field, it's vice versa.
Why is there a line like this?
Why is the line? Sorry?
Why is there no vertical line? I mean, there's a horizontal one when the bottom gate is 0 and the top gate is early. No, it's not symmetric again.
Oh yes. That's a very good question too. So basically, there is a conversion from gate voltage to electrical field or displacement field and carrier density. So in this gate voltage, the resistance peak is lying in this direction. Okay? So if you make a line cut from here, you've got a bottom gate dependence resistance peak. If you make a line cut from here, you get a top gate dependence resistance peak. And here there are two gate voltages acting together to your graphene. So this is a binary graphene. There's a dielectric on top. There's a dielectric in the bottom. There's a metallic plate on top, and there's a metallic plate in the bottom. And this guy is grounded. That's the experimental setup. You have a voltage here, a voltage there, which is with respect to the ground there, and they are self-grounded also to have this potential applied. You basically have two capacitors there. And if you use VTG minus VBG, so the two signs give you a definition, there's some kind of a parameter for that, a definition of electrical field. And if you use this VTG plus VBG, there are some prefix there, let's forget about that. There's a beta. So if the two are identical, then they're just one. If not, otherwise the ratio is slightly different. So this one defines the carrier density, this one defines the electrical field. If you do that on conversion, you will get the resistant peak vertically lying there. So this map will be just linearly transformed. That means everywhere you sweeping this axis of n, which is a sum up of two gate voltages. That's a sum up of two carrier densities, right? Because we are linearly converted into carrier densities. It's just C capacitance times Vg is equal to Q, right? So Q is carrier density. And everywhere in this axis, you have a same constantly doped carrier density. Everywhere in this axis, you have a constant electrical field. That's why they have a lines this way.
So it's just current by the capacitance?
Yes, it's just a simple capacitance coupling. Nothing big deal. Yeah.
I have a question.
Yes.
Why is it important to find the gap in graphene?
Sorry?
Why is gap important in graphene?
Why is gap is important? Let's say it's not that critical for fundamental research. For applications, you need a gap, especially for nanoelectronic applications, because you want some transistor which can work on an on-state and off-state in a stable manner, right? Say you put a voltage, it's on. You put another voltage, it's off. You don't want the off to be halfly off and still semi-on, things like that. A very good transistor should look like a step function, the ideal ones. And that's actually how people can obtain in silicon transistors. They're very good. If you look into these commercial ones, their curves they are rising really rapidly in very small range of voltage, and you obtain saturation current. Here it's really off. Like on-off ratio can be 4, 5, 6 decades. For graphene, if you don't have a gap, you can, for example, here you are in this valence band, you have holes. At this point, you are at the minimum of densitive states. This is DOS. Looks like dispersion, but it's DOS, okay. And then after this one, you are entering this conduction band. So you are conducting again. That means if you want to use graphene as the on and off, the off is only here. It's very narrow, cannot control that. Also, graphene is very sensitive to the environment. The whole curve can wobble this and that. That means you cannot really use them in a large scale. For example, 1 billion of graphene transistors. Every one of them has to have a very well-defined off state here. It's almost impossible so far, even for other 2D materials. I'll talk that later. Even for TMD materials, it's so difficult. So far, yes.
Okay.
Right. So this thing might be interesting for you theoretician guys to look into this paper and discover what's going on there, why the graphene, in their case, is more resistive and wider in the gap region, which they claim to be a very good semiconductor, I mean, among graphenes. And this is in the meantime, in 2011, somewhere here, people found that graphene is desperate and graphene is useless. it has no band gap. It's not useful for any kind of real application. So a group of people just heading toward another direction. They found that maybe traditional metal dicarbonate is the future. For example, this is a famous paper published by Marquis in Switzerland. They found that using the same exploration method of very thin, atomically thin MOS2, you can also construct transistors. Now there is no bipolar behavior. The off is really off, and the on is always on. It looks like a silicon transistor. So it might be really useful. And they published another paper after this one and tested the high frequency behaviors, tried to grow them into large scale and so on. I think we'll give more details in lesson 3. That means at least from 2011, people have found that graphene should be somehow changed, and let's do something else. And like a significant amount of people have already switched from graphene to TMD. So even today, if you are, say, in a conference, you say you are still doing graphene, it will be really surprising to people. Anyway, so then the third question for today is, we already went through a brief history of how it was invented theoretically and experimentally, and there was some side stories happening. The transfer worked, and then the TMD started to work. But people never gave up to make graphene cleaner from then on, from the first day of the discovery of graphene photovoltaic transistor. So there are really good experimentalists trying really hard to make graphene cleaner. And let's say, again, let's take the time capsule. If you were the experimentalist, how would you do to make your graphene cleaner? Can anyone give me some example? Hello? Please. You have the opportunity to
Sandwich it with something.
Sorry?
Sandwich it with something.
That's great. That's great. Yeah, sandwich graphene in some kind of cleaner substrate, for example, and
Is that a good big industry to
coming through.
the bigger industry that has not more money to use more efficiency?
Okay. That's a good, also very smart idea to throw more money into the industry and let them work hard, right, to get the graphene cleaner. But they already spent a lot of money. Apparently it didn't happen. So there is a reason. To make graphene cleaner is a very difficult task. You know that graphene is a purely surface, right? It's two-dimensional, surface everywhere, and it's anything you put on top of that scatters the electrons and degrades the quality. Apparently, people have thought about this question in around this period because graphene has been discovered, theory has been developed, everyone seems to be happy on the side of theoreticians, but experimentalists are not happy, we're not happy, and are not happy now. We'll not be happy even in the future, I would say. It's a pessimistic prediction. Let's say, there is a very famous naive model to tackle the problem of electron motion in an environment. It's called the Zheng model. So the Zheng model says your electron has a mean free path. So once upon a time, it will be collide into some other electron or kind of impurity, anything. So there is a very short amount of distance. It's flying ballistically. Okay, so it's defined as a mean free path. So at the end, electrons are drifting in a velocity, which is called drift velocity, defined by this mobility times electrical field. That's how it says. So apparently, in graphene, it's the same case here, except that all the conditions are now two-dimensional. So we have to reduce the impurities, like, for example, encapsulate somewhere graphene into there. Also, we have to make the surface flatter. Why? Because any kind of fluctuation in z dimension will scatter your graphene. Or kind of, the tension defects, or even long-distance Coulomb interaction, Coulomb scattering, will degrade your graphene quality in terms of electron mobility. Okay. So then, there's two ways to make graphene less scattered. Once it's reduced the dimension of the device, that is, make the device smaller than the mean free path, then everything is ballistic. Please.
What do you mean by laser picture?
Sorry?
What do you mean by less?
It's just when it's placed on top of some kind of piezoelectric environment. For example, the many materials, they have sliding ferroelectricity. Make graphene hysteristic. Actually, I have to. These slides I took from Korea, so at that time he was considering this scattering. To be honest, it's a good question. I will check that later. So anyways, to have the graphene less scattered, we have two ways. One is to reduce the size of the system, to have the system smaller than the mean free path. Then then electrons inside of the system will not have any chance to scatter with anybody before it reaches from the source to the drain. And also, there's another way, of course, is to increase the mean free path. Increase the mean free path seems to be harder compared to reducing the device size, right? And at that time, people have did a lot of investigations using STM and other techniques. For example, this is just to evaporate some dopants on top of graphene. At the same time, there's a shift of direct peak. That means your Fermi level is moving, and also the slope of conductivity is decreasing. That means the mobility is degrading also. And there are also some STM studies showing that there are a lot of inhomogeneities in the microscopic scale. That, for example, this is the electron hole puddles, very famous picture, that even at the direct point, you have fluctuations of electron holes. And which gives actually another story behind. There's a minimum connectivity, which has been puzzling people for years. And then there are ways to, for example, for 3D bulk material, there is only one surface on top. So some kind of impurities are screened, and they cannot influence the inside body transport. But for two-dimensional systems, it's all surfaces. So we cannot avoid any kind of impurities because long-term, long-range and short-range scattering can both degrade your transport properties. And the first way people found was, let's get rid of the substrate. Let's just suspend graphene so that it's flying freestandingly in vacuum, so that by passing some current, you will heat it up to a very high temperature. All these residues will just be evaporated, and graphene will be pristine. And that's a very simple thought experiment, and that's how people did at the very beginning, 2008. And indeed, you can see that the blue curve was this suspended graphene flake before annealing, and the red one is after annealing. That means all these surface absorptions or residuals are killing this transport from the red curve into the blue curve. So it's a very good example saying that if you suspend graphene in vacuum and you can get rid of the surface degradations, you will have a very high mobility. Here is 230,000 centimeter square per volt per second. It's almost comparable to quantum Waals systems. All right? And using this technique, people found that there were the first experimental evidences of fractional quantum Hall effect in graphene. There's also people found that when graphene is suspended, there will be stronger interaction, and this will be our details for the next lecture. Using this kind of interaction-driven phenomenon, we can really devise some new devices out of graphene. And here's another way people found, instead of getting rid of the substrate, which is very sophisticated and the yield of sample is very low, it's not very practical, not everyone is happy to using that kind of technique, and it's fragile too. So there is another way, like your name? Like Dima said, if he was at the time of 2010, he would try some substrate to replace silicon oxide, because we saw that silicon oxide has a lot of roughness and dangling bonds. So then this famous material came out, which is a hexagonal boron nitride. People found that to have a very flat surface without dangling bond and clean, it has to be an inert two-dimensional insulator, right, for graphene. So there are already, this kind of condition already limits a lot, sort out a lot of materials. There are not many left. For example, boron nitride is one of a good example. It has a band gap of around 6 electron volts, which is very insulating, and dielectric constant close to silicon oxide. You can use that directly as a dielectric constant material to get your graphene system. And also it has an atomically flat surface because boron nitride is also a two-dimensional material. The fluctuation at Z is the fluctuation of the atoms, the very, very small fluctuation in Z. And that's how people do. Actually, my postdoc supervisor did. Corradine found that if you use this wet transfer method of how you fission graphene, then you put this first fission graphene method combined with this landing technique of under a microscope, landing the graphene flakes on top of a boron nitride, then you will have a heterostructure ever made for two-dimensional systems. And magically, you will see that this is also annealed, all right, okay, because there is only one surface supported by boron nitride. And then you will have this black curve as a field effect of graphene. And there you got a mobility of 100,000, which is already very good and comparable to suspended graphene, comparable to gallium arsenide, quantum weld. And this is there's a review paper talking about this, the mechanism behind. Because on silicon oxide, a graphene is lying in a rough surface with a lot of dangling bond, and on hexagonal boron nitride is atomically flat and it's clean, there's no dangling bond. So we have a very homogeneous spatial distribution of charges. So that's a big story at 2010. So we have to mark this one down here. I think it's 2010, yes. Boron nitride graphene has merged. They found a way to combine themselves and demonstrate very high mobility graphene, and which is still, even after more than a decade time, everyone is still doing the heterostructures of two-dimensional materials using the same method. So this is a graphene on HBM, how it looks like. Okay. We already said that it works for monolayers and bilayers both, and there's a huge enhancement of electrical performance. And people found then using this technique, you can also see fractional quantum holes. And this is how it worked experimentally. Basically, you have a transparent stamp, which is a kind of a gel, let's say PDMS, for example. And then you stick some kind of a PVC on top. Using this microscope, you will be able to see each layer of materials and just align them because they are very large scale in size. It's just like 10 or 20 micron, but it's already big for a two-dimensional community. Okay, and you can do this repetition of stacking method. You can just do your any kind of demanded heterostructures vertically assembly. At the end, you just melt all these polymers and do an annealing in vacuum. You'll have a very clean interface. Looks like this one. This was taken from Corey's paper. So the previous discussion was on how to get rid of scattering impurities of graphene. So people found two ways. One is to suspend graphene. The other is to find a substrate. So one substrate apparently is not enough. So Corey later on in 2013 developed a beta version of this technique that using this dry transfer technology instead of the wet transfer before, you can use the stamp, like I described this one in this slide, to do the whole stamping together again and again, and you have a sandwich-like material vertically assembled. And this is how it looks like under this TEM microscope. You will have a boron nitride on top and boron nitride on the bottom, and there is graphene in the middle. So you just put a metallic contact using this side contact technology, and then the contact resistance is very good, very low, ohmically, and you will have a beam free path here, amazingly large. For example, with a device size of 20 micron, you almost have a beam free path of 20 micron. So it's limited by the size of your device, not by the scattering anymore. Of course, that is limited in low temperature, because at high temperature you still have photon scatterings, okay, which cannot be killed by the substrate. So a sign of very high quality is this one. Is the blue curve, there is a negative resistance. So that means your system is actually ballistic in this configuration. People can obtain ballistic system of electrons, which is direct from use. in the scale of several tens of micrometer. That's amazing, just a few tens of years from the very beginning to now. So up to this point, we can just come to this slide that the new era of additive manufacturing has been invented. Before it was just subtractive manufacturing from, let's say, early 90s to 2010. And people are just racing to exploit all kinds of material down to thin limits. And from this time scale, everyone is trying to look in another dimension, is to building these atomic Legos vertically up to have these heterostructures that does not exist in nature. This has to be man-made. And because they have a very open surface, they are clean, they are easy to exfoliate, and there is no lattice match needed in the system. So there are literally unlimited possibilities of this system. And that will go through also in later lessons. So with this in hand, we have a system which can, two-dimensional materials can be piled up vertically, which can be spaced by some kind of insulator to study this Drax phenomenon, excitons phenomenon, etc. And we can also have twisting, which is, for example, if you really want to name a specific point of graphene of two-dimensional materials compared to, which is distinct to 2D, to 1D, 0D, and 3D, is that in two dimension you can have a twist in between two surfaces. And these two surfaces, because of the lattice match or mismatch, will have a new Moiré superlattice, which will modify electronic structures which can never happen in 0D, 1D, or 3D. So this is really something which is specific for two-dimensional systems. I think we have enough for today. It's 5:30, right? And tomorrow I will go through something more about quantum polish later in graphene, and later on about other high mobility two-dimensional semi-metals and semiconductors. Thank you so much.
So next talk is the process technique. You also decided 7:40.